Hello guys, can you hear me?
Warning.
Okay, seems like I can see myself. So, how was the contest today, guys? How was the contest for you? How many problems you guys solved today? Hi, Faizur. Let me bring the comments. 2 problems. Okay. I unfortunately could not participate in the contest today, but I thought about all the problems. At the beginning of the contest, I had some work, but I read all the problems and I think I have solution for all the problems. So we will discuss all the solution of all the problems from A to E2. This was a good contest, I think. So C was too tough to handle. What's the C? Thank you very much. Volume. Sure. Sorry. This issue keeps happening, and each time I need to go to setting and fix it manually. How's the voice now? Let me make it a bit. How's the voice now? Good? Awesome. Awesome. Nice. Nice. So, without any further ado, shall we start talking about problem A? Start with problem A, and we're gonna solve all the problems one by one. Let's go. Good. Okay. Then let's start. We will go to problem C. Let me first start from the beginning, and we will cover all the problems. So, the first problem says that you are given 3 integers x, c, y, c, and k. You need to find k distinct points in a way that the center of them, which is the average of their x's and the average of their y's, will be xc and yc. You need to provide these points. Okay, how can we solve this problem? Well, in this problem we can say that, let's say that center is here. This is points, this is our center, points xc and yc. Well, I say that if this is your center, there are 2 ways. There are 2 cases. Either your n is odd, your k is odd, or your k is even. If your k is even, what you can do is to just, first of all, you can just consider this specific x, and you can choose all of your points from this specific x. If k is even, just put 1 point here, just its x is equal, its y is 1 more than your center, and 1 in here, its y is 1 less than your center. 1 in here, 1 in here. So this is xc plus 2 and y, sorry, xc and y, c plus 2. This is xc and yc minus 2. And so on, just continue this. I mean, you need to have k half here and k half here, k half points here and k half points here. And this is how we can solve it if k is even. And if k is odd, you need to just add 1 more point on the center itself. And these k halves will be rounded down. And this way you will have k points such that their center is point xc and yc. And that's going to be all about this problem. Is it clear? If you are okay with that, you can use this emoji or put a plus in the chats. And if any part is not clear, you want me to explain it more, tell me to explain more. Okay, nice. So shall we move on to problem B? Yes, I will talk about this mostly in, I think it's better if I talk about it in the live streams that we have on Fridays. Fridays from 12 to 14 GMT, if you don't know it already. Friday from 14 to 12 to 14 GMT, we have live topic streams. In those topic streams, we will talk about those things. Okay? So, let's start talking about problem B. Let's bring it. So, this is problem B. This problem says that you are given a permutation P of length n, and you need to find a permutation Q of length n that maximizes the number of, that minimizes the number of pairs such that the sum of this interval, for example, pair of ij, such that the sum of this interval in P is equal to the sum of this interval in Q. You want to minimize such pair of I and j's. Okay, so you want to have it as few as possible. Well, on this problem, the first thing that I say is that the answer, our answer, is going to be at least 1. Because whatever you do, the whole permutation have the same sum in both of them, in both P and Q. In both of them, the whole sum, the total sum is going to be 1 plus 2 plus 3 to n. So it's going to be equal. So the answer is at least 1. I want to also show that the answer can be 1. So correct me if I'm wrong, but after reading this problem, this is what I think. If there's no issue with this, the answer is only 1. Why? Because for any Pi, I can set Qi as Pi plus 1. And if Qi is equal to n, if Pi is equal to n, this is the case where Pi is less than n. And if Pi is equal to n, I set Qi equal to 1. Okay, so it's like I'm rotating all the numbers. N goes to 1, 1 goes to 2. So this is gonna be what happens. This is the numbers that I have. 1 goes to 2, 2 goes to 3, 3 goes to 4, n minus 2 goes to n minus 1, n minus 1 goes to n, and n goes to 1. So it's like I'm rotating everything. It's modulo n, I'm adding 1 to all the numbers. If I do this, I want to show that any interval with length less than n is gonna have different sums in the two permutations. Why? Because if you consider, why it doesn't write? Okay, this is bad. Sometimes this issue happens. So I'm saying that if you consider two intervals in the first permutation and in the second permutation, what is going to happen is that if n is there, there are two cases. Either n is there or n is not there. So let's get back to tablets. Either n is there or n is not there. If n is there, you already know that for that element, here you have n, here you have 1. So the sum of, because of this element, the sum of q will be added by 1, the sum of p will be added by n. So the difference will be added by n minus 1. So you need at least n minus 1 more elements so that it would make up and they would be equal again. So in this way, you need all the elements. So if n is there, all the elements must be there, because you need at least n minus 1 more elements. You need n minus 1 more elements at least, so that these elements will make up for the difference that n has made. Okay. And if n is not there, we know that for all the elements in here individually, what is in Q is greater than what is in P. So Qi is greater than Pi. So this total sum is also greater. Okay, so we can say that in this way it's not possible that they have the same sum, therefore the answer is gonna remain as 1, and this way the answer is 1. It's only possible that their sum is equal if we choose the whole array. Does it make sense? Again, please, if you're okay with that, again, please use this emoji or put a plus, and then we will move on to problem C. It is not clear? Yes, so that's the same thing. We will rotate everything to right. Shall we move on to problem C, or do you need more explanation on problem B? Okay, so more explanation for problem B? Okay, so let me just talk a little bit more on problem B so that all of you are okay, and then I just for a minute, I will continue talking about problem B just for 1 additional minute. I'm just saying that if you consider these two permutations, P and Q, I'm saying that set Q of I as P of I plus 1 only if P of I was n set it to 1. So in other words, it's like you set Q of I as Pi modulo n plus 1. So this is what we're doing. We set Q of I as Pi modulo n plus 1. If we do this, if you consider an interval, now I'm trying to explain in another way so that if you understood the first solution, this is going to be a new solution for you. So I'm saying that if you set it like this, I'm going to provide another proof. If you consider any interval, consider that the length of this interval is L. So if you consider the sum of P in here, in this interval, it is some X, and consider the sum of Y in this interval, assume that it is some Y. Well, I want to show that if the L is less than N, the length is not N, X is not equal to Y modulo N. So the sum here and the sum here, instead of X and Y, maybe it's better if I use S1 and S2 so that it's more obvious that these are sums that we're talking about. So S1 and S2 are not going to be equal modulo N. Why? Because you can easily see that in each point, each element, this specific element in Q modulo N is 1 more than that specific element in P modulo N. So if you add these values up, you can say that S1 plus L modulo N is equal to S2. Because the length is L, and at each point we're adding 1 to our elements. Modulo N, we're adding 1 to each element. So S1 modulo N is going to be S1 plus, S2 modulo N is going to be equal to S1 plus L. And we know that this can only be, S1 can only be equal to S2 if they are equal modulo N as well. The remainder to N must be also equal. But that can only happen if L is equal to N. Only if L is equal to N that can happen. Let me write it like this. Only in this case it is possible that S1 is equal to S2 modulo N. And only if S1 is equal to S2 modulo N, then it is possible that they are really equal. So the point is that when you add 1 to each of these elements, you're adding 1 to the sum modulo N as well. And if L is less than N, these two sums will not be equal modulo N. So they cannot be equal as well. So this was another proof for it. Is it clear? Yes, this proof was a bit more advanced, and maybe in some more advanced problems, a proof like this can be more helpful. Yeah, awesome. So, and guys, you can always see any part again. For example, if you come here Any part of the live stream can be watched again. If you can choose from here and you can watch any part of the live stream again, and after the live stream it will be recorded and you can watch any part if you want several times. Okay, so feel free to just check any parts again. So let's move on to problem C. Problem C. Perform operations to maximize the score. You are given an array A of length n and an integer k. You are also given a binary array B of length n. You can perform the following operation at most k times. Select an index I such that bi is equal to 1. Bi is either 0 or 1. Bi is a binary array. B is a binary array. And set ai equal to ai plus 1, or increase ai by 1. And your score is defined to be maximum of ai plus median of ci. And ci is the array if you remove ai from it. You want to maximize this value at the end. So you want to maximize the max of ai plus median of ci. Right? Your score is maximum of this, and this maximum itself, you want to maximize it. So you need to say that what is this maximum score that you can get. On this problem, what I say is this. You can, if you consider the array, there is exactly 2 possible medians that you can have. So for your median at the end, there will be exactly 2 choices. And your median will always be one of these 2. Do you agree with this? So, I mean, any element that you choose and remove it from your array, in your CI, your median is one of these 2 options and not anything else. Okay, so it always is one of these 2 choices. Now, what I will say is that there is a prefix till here. If you remove these elements, your median will be this. And if you remove these elements, any of these elements, your median will be this. Okay, so there is a prefix until this first median itself, such that if you choose them, your median will be the right one. And there's a suffix that if you choose them, your median will be the left one. Okay. So now what I say is that let's consider these 2 cases individually. If your median is this, or if your median is this. There's another fact. So this was the first fact. Fact 1. There are only 2 choices. Only 2 possible. There are only 2 possible final medians. Okay, this is the first fact. Yes, the first fact is that there are only 2 possible final medians. Because assume that you remove the first elements. What is gonna be your median? The indices will be like this. This is the first element, this is the second element, and this is the element number n minus 1. So your median will be somewhere, for example, in here. And if you remove the last elements, the indices will be like this. This one will have index 1, this will have index 2, and this will have index n minus 1. So indices will be shifted by 1. So your median will be shifted leftward by 1. So the difference between if you choose the first one and remove it, by the first one I mean the smallest one. Okay, because you can sort all the elements. It doesn't matter. Initially I can sort all the elements. Because their order does not matter. The order in the inputs does not matter. So I sort all the elements. And I say that if I remove the first one, the smallest one, my median will be something. If I remove the last one, my median will be shifted to the left. Okay? And now I'm saying that for all the other indices, I mean for everything in here, your median will be this. For everything in here, your median will be this. if you remove them. So is fact 1 clear now? So the fact number 1, the first fact is that there are only 2 possible final medians. Yes, that was exactly what I was talking about. I'm saying that if you sort all the elements, from the smallest one to the greatest one, if you remove the first elements, now the indices of the the rest of the elements, starting from the smallest one, is going to be 1, 2, 3, 2, and minus 1. What is going to be your median? Your median is going to be elements with index n half. N minus 1 plus 1 half rounded down. If you remove the last element, now your indices will be this 1, 2, 3. So your indices will be shifted leftward by 1. Now your median will be the index n half again. But if you see the indices are shifted leftward. So now this one is n half, index n half. It is exactly shifted leftward by 1. Because all the indices are shifted leftwards by 1. So the difference, if you choose the first one and remove it, or you choose the last one to remove it, the median will move only by 1 element. And now it's not only about the last element. If you consider these 2 medians that removing the first element and the last element will give you. Consider these 2 medians. I'm saying that if you remove anything in here, then this one will have index n half and will be median if you remove anything in here. And if you remove anything in here, then the index of this one will be decreased by 1, and this one will have index n half. So there are 2 possible medians that we can have. If you remove an element from here, from index 1 to the first possible median to index n half, your new median will be this one, the one that originally was at index n half plus 1. And if you remove anything from this part, this will be your median, the one which its index was n half rounded down initially. Originally n half. So is it okay now? If you're okay with that, please again put a plus or use this emoji. So this is fact number 1. This is going to help us. Is case 7 okay with this fact? I have not seen case 7, but this fact is always correct. So anything that case 7 is, this fact is correct because we've proved it. We've proved that always this is correct because we showed that if you remove the last index, we showed that if you remove the last index, your median will come here. If you remove the first index, your median will be here. And then we showed that because your median after that deletion will be an element with index n half. So the question is that after your deletion, which element has index n half? If you remove anything from here, the indices of these ones will be subtracted by 1. So this one will have index n half rounded down. But if you remove something from here, this element will remain at index n half because not itself and nothing before it is removed. So it will remain at index n half. And this one is the median. So always median is one of these 2 elements. For explanation, I use 1-base indexing, but in code you need to use 0-base indexing. It's better if you use 0-base indexing. But in explanation, I can say that my median is either the elements with index n half rounded down or n half rounded down plus 1. Okay. So this is the first fact. Now, after that, I say another fact. I say that consider the I, the index I you'll choose. The index I you'll choose. I'm saying that this is fact number 2. I'm saying that if b sub I is equal to 1, then you will always increase a sub I. You will always increment a sub I. So I'm saying that if the index that you will choose at the end, at the end, when you maximize your score is calculated based on some I. I'm saying that the answer is optimal if all of your operations was on that I. Otherwise, you could just change your operations and just each time choose that specific AI, and your answer was still as good as what it was before. So I'm saying that as fact number 2, I say that if you choose an element and remove it, at the end your score is calculated based on some I. Assume that we've done all the operations and see that our answer is calculated based on this I. Okay, our answer is calculated based on this I. I say that it is always optimal. Now we can change the operations, and each time, whatever we chose, instead each time we just increase AI. Then our final score will be at least as good as what it was before, because this I itself still gives us the same thing, at least. And therefore our maximum for every I will be at least as good as what was before. Why? Because if you do this, you make sure that by each increment, your final answer is also incremented. Your final answer is also incremented. Okay, so by each increment, your final answer is also incremented. And that's the best possible thing, because if in each operation you can increase your final answer by 1, that's the maximum you can do. You cannot increase your maximum answer by more than that. So if you're gonna do an increment, do it on a sub I. If b sub I is 1, you can only do this if b sub I is 1. So do it on AI. So this way you make sure that your answer will be increased by this operation. Is this also clear? So this is my fact number 2. This is my fact number 2. AI is the index. I said assume that I is the index that you will choose at the end. I is the index that you will choose at the end. So I'm saying that if b sub I, at the end you want to maximize, the value of AI plus median of Ci for some I. So I'm saying that when you do the operations, you will choose some I and calculate this for that I. Consider that I, if for that I, bi was 0, it's always optimal that if from the beginning you would do all the operations on AI. Okay. Awesome. So this is fact number 2. And the fact number 3 is that if we're gonna remove, as I said, we have 2 cases. Either our median at the end will be this one or will be this one. I mean, there are two possible medians that we can have. Now let's consider these two cases separately. Assume that our median is gonna be, for example, this left one. This means that we need to choose something from here. We need to choose some element from here. And if we have two I and j, so I'm saying that consider that we are going to choose an index from the right side. From the right side. The side that if you choose it, you're gonna end up with the left median. Then, if you have two I and j, if you have two for an I and j, for I and j, if their b is equal, I mean they don't have any difference in their b. bi is equal to bj, it is optimal to choose the one with greater, value of a. With greater value of a. Or let's say, it is better to say that if bi is equal to bj and without loss of generality, I is less than j, and I is less than j, it is optimal to choose j over I. So all I'm saying is that if you have two indices that you can choose from and their b is equal, I mean, so they have no differences according to b, it's always better to choose the one that is greater, because their b is not different. So it's better either you can change both of them, or you cannot change any of them. Let's consider the one, if you cannot change them, it's better to take the maximum one, because a greater value will be added to median at the end. And if it's not, again, if you can increase them, we know that all we do increase is that value itself, so it's better if we start from a greater value. So I'm saying that it's better, so you can somehow consider it as fact number 3. That's always better if you choose the one that is greater, if their b is better. So now I'm saying that if you consider the right parts, so this is the more useful thing that I'm gonna say at the end. If this is your left median, and you're gonna choose your AI from here, and you're gonna end up with this left median, I'm saying that if b of n is equal to 1, if b of n is equal to 1, from right side, in the case that you want to choose from right side, it is also possible that you will choose from the left side, but from right side, the best option is n. I'm saying that if bn is equal to 1, you can choose, if you're gonna end up with this median, the best thing is to start from an. This way, an plus this median is initially maximum possible, maximum it can be, and with each operation it will be increased by 1. So we have the maximum that we can ever have. So if we're gonna choose from the right sides, and b sub n is equal to 1, it's always optimal to choose n, and each time increase it by 1. This way we start from the maximum possible, median is added by the maximum possible value, and also each time it will be added by 1. So also k will be added to it, and k is the maximum number that can be added to it. So this is the main important fact that I will say about this problem. If b sub n is equal to 1, from right side is always the best option to choose n. The best option is choosing n. Is it clear? So if b sub n is equal to 1, then always the best possible option from the right side that you have is to choose the last one, because you start from the greatest value, the greatest possible value, and each time you're increasing this value by 1. So your answer is gonna be the best you can have. Okay. I could see fact 3 but not fact 1 and fact 2. You say that fact 1 and fact 2 are not clear. Fact 1 and fact 2 are not very complicated. Fact 1 was that we have only 2 possible final medians. And fact 2 says that consider some I, you will if bi is equal to 1, you will choose some ai. I mean, if you consider the last I that you will have, you will always increase that ai. Oh, I see, during the contest. Okay, good. So what I can say is that if Bn is equal to 1 from the right side, the best option is n. The same thing can be said about the left side. I mean, if you're gonna choose some element from the left side, and your median is gonna be this right median, if you consider this last element, the greatest number that you have in here, this left median, the one that is at index n half, you can say that if b of b sub n half rounded down is 1 from the left side, the best option is n half. It's you know, the solution might look a little bit long, but it's because I'm explaining it. In context, all these facts can come to mind very faster. I mean, at the end, when I gather everything up, you see that it is not that long that it seems to be. Right now, because I'm trying to explain each part in details, it might look a bit long, but it is not really that long, etc. At the end, when we gather everything up, you will see that it's not that long and complicated. So about this, it is the same thing as we've seen here, just it is about the left side. This one is about the right side, it's about the right side. This one is about the left side. So again, I'm saying that from the left side, if the maximum value on the left side has b of that one is 1, it's always optimal to choose that one, because this is the maximum thing that can be added to the right median, and this way each time also we can add 1 to it. So this is gonna be the maximum that we can get at the end. Is this one clear as well? If so, now we should see what happens if b is equal to 0. Awesome. No. If we increase the left elements, this element is removed from our array. You know, the point is that this left element is removed from our array. So increasing it does not have any effect on the array, on the remaining array, and it does not change the median of the remaining array, because this element will be removed from our array. So because this is going to be removed from our array, it doesn't have any effects on our median. Okay. So no, I'm explaining C right now. If you want, you can maybe see that part that I started C. Watch that part. So I'm saying that now consider that if you consider these two medians, now consider that b sub n is equal to 0. What happens if b sub n is 0? Well, the point is that at the end, when we choose, assume that this is our left median and we're going to choose this left median. So we're going to choose someone from here. As the fact that we saw here, I mean, if you see the fact that I was seeing in here, if b of two elements are the same, the greatest one is better. So this was the best option for b equal to 0. This is the best option for b equal to 0. And the best option for b equal to 1 is the first one that we have in here. So if we consider the case that we can consider the maximum I such that bi is equal to 1, that is the best option we have for bi, for the case where bi is going to be 1. And for that case, we can calculate what is the sum of that one and the left median and add k to it, because at each element that will be increased by 1. So that's the case if you're going to choose bi is equal to 1. But if we choose n itself, if we choose something that's its value of b is 0, now the point is that we cannot increase this. We need to somehow maximize this median. So the question is that what is the maximum median that we can have? Okay. And how can I solve this? How can I find that out? I know that if bn is equal to 0, I mean, if I'm gonna remove something from the right side such that its value of b is 0, I'm gonna remove the last element. So I know that only the last element is gonna be removed. I'm sure that if I'm gonna remove something such that its value is 0, is b is 0, it is the last element that I will choose and remove it. So now the question is that how can I find maximum x such that all these elements except the last one does not matter. The last one will be removed. The last one is the one that has bn equal to 0 and it will be removed. Because if the last one had b equal to 1, it would we are sure that we would choose that element and each time we would increase that. But now this is the case that bn is 0 and bn will be removed. So all the elements here from this index n half to elements n minus 1, all of them we should find maximum x such that we can be sure that we can make sure that all of these elements will be greater than or equal to x. Because our median is gonna be the minimum of these elements at the end. So minimum of these elements from here to the end is gonna be our median. So we want to, it's like we want to maximize this minimum. Right? So how can we maximize the minimum of some elements? Well, the first idea that comes to mind is to use binary search. That is something I think maybe it can also solve without binary search, but the first idea that comes to mind is to use binary search on x. This way we can fix x and try to make everything greater than or equal to x. This way we can fix x and make everything greater than or equal to x. And after doing this binary search on x, we can find out what is the latest elements less than x. Okay, we can find out what is the latest element less than x. Okay. And all of these elements must reach x. All of these elements that we have in here must reach x. So we have another binary search, like another binary search, to find the latest I such that ai is less than x. Because if we have these elements all must be increased and reach x. Because right now their situation is not good. They are less than x, but I want all of these elements to be at least x. And using a prefix sum, I can then find out what is the sum of this interval and how much do they need. Also, I can have all the indices that are 0. For example, I can have another prefix sum that computes the sum of bi's or saves the number of zeros. I mean, it stores that in this prefix how many zeros do I have. Well, the point is that in here I must not have any 0. Because if I have any 0, it means that some ai is less than x and you have to increase it, but you cannot increase it. That's bad. There's nothing you can do that way. So you need to make sure that the number of bi's in here is equal to the number of bi equal to zeros in here is equal to the number of bi's equal to zeros in here. So that in between you have no additional elements with bi equal to 0, and you need to, what is a prefix sum? You can find out what is the sum of this interval and how much do they need in total. For example, if there are L of them, they should reach Each of them should reach x, and from this we can subtract the prefix sum of that part, pref of r minus pref of l. So this way you can see that how much it needs, and if it was less than or equal to k, we can reach x, otherwise we cannot reach x. And this way you can use a binary search to find the maximum possible x. This is the case if bn is equal to 0 and we want to choose something from the right side. Is this part completely clear? Do you have any questions about this part? Let me see the comments. Okay, I will explain it again. Why do we need to binary search on x? Can we not greedily find the largest AI in the right side? If bi is equal to 1, we're done. Yes. If bi is equal to 1, the problem is solved. Because we find the largest AI in the right side, which is bn, and the sum is equal to bn. That is the previous case that we were discussing. In that case is done. Now I was discussing the case there bn is equal to 0 and everything is sorted. So maximum is bn. I sorted the list. And if bn is equal to 1, yes, as I said from the right side, the best option is n. We will have this one plus this median and add k to it. That part is clear. Now I was talking about the case that bn is equal to 0. About the rating of this problem, I'm not sure about. This problem was mostly implementation, I think, because it doesn't use very genius ideas. It's about just considering the cases and implement all the parts. I personally do not love this type of problems. I prefer another types of problems, but yeah, it is like this. Why can't we add 1 to the left of the meat? Because it has no impact. We can do that, but you know, the point is that if you want to have your median to be at least x, at least half of your numbers must be greater than or equal to x. So if you want your median to be x more than, in this problem, more than half of your elements must be at least x. So the same is here. We need to make sure at least half of our numbers, at least these many numbers, are at least x. We can increase numbers from the left side of median, but if we want to make half of the elements greater than or equal to x, it's better to start from the elements that are already higher so that we need less operations. So we can increase these ones and make sure that these ones are greater than or equal to x as well. But it's better if we work on these ones, because these ones are already greater and our job is easier to make them greater than or equal to x. So if you use, if you want to make at least half of the numbers greater than or equal to x, it's better if you focus on these parts. It's optimal, it can be proved that it is optimal to try to make these ones greater than or equal to x. Therefore, we just focus on these ones. We do not try to make these ones greater than or equal to x. We don't care about them. We need half of the elements to be at least x. Which elements are the best to make them at least x? The ones which are already higher. So we only try to make them at least x. And we only need half of them to be x. So we do not need more than that to be x. Okay. So what if b sub n minus 1 is 1 and bn is equal to 0? I explained that part as well, but I will explain again. I don't understand this. What if there are 0 in the right? But what if these elements do not have bi? Okay. Let me explain this again. Explain it in more detail. So let's assume that when we have this array, I'm saying that we have two medians, two possible medians at the end. This is what we discussed and we are all okay with it. Assume that we want to use the left median. So the elements that will be removed must be in the right side. First, I said that if Bn is equal to 1, the problem is done. We will choose Bn along this median, and each time, each operation, it will be increased by 1. So this case is done. This case is easy. If Bn is equal to 1, the best option is always to use this one, and this case can be solved easily. Okay, each time it will be added by 1. But if Bn is equal to 0, this is the case that it must be harder. So we choose from the right side. This is the case 1 that we choose from the right side. We said that if Bn is equal to 0, everything is good. But if Bi is equal to 0, again there are two cases. Either you will choose n, or you choose the maximum I such that B sub I is equal to 1. Okay, so this is the answer to one of your questions. Either when Bn is equal to 0, either we choose n, or we choose the maximum I such that B sub I is equal to 1. If we choose the maximum I that B sub I is equal to 1, the current answer is sum of these elements as this and this element, A of I and A of n half, and every time it will be increased by k. So this can be easily calculated as well, and we have this answer. But we need to find the maximum of it and the case where we choose Bn. And the case where we choose Bn. Okay. So now we are focusing on the part that B sub n is equal to 0, and we want to see that what happens if we choose B sub n. Okay, is your question answered? This question that you asked here? We fix the I that is maximum and B sub I is equal to 1, and we consider the case that those two elements will be chosen. We consider the case that those two elements will be chosen. I mean, this element will be chosen, and we have the left median, and each time it will be added by 1. So in total, it will be added by k. Right? I mean, is it clear? If it is clear now, if it is clear now, I say I want to consider the case where B sub n is equal to 1. I know that here I'm in the case that B sub n is equal to 1. B sub n is equal to 0, and I say that all these elements I need to maximize my median. First, let me say this. I need to maximize my median because an cannot be added. I cannot add anything to A sub n. So I need to maximize my median. And let's say, so in order to maximize our median, I need to answer this question. What is the maximum x such that my median can become x? So this is my question. What is the maximum x such that my median can become x? Now I'm saying that let's do binary search on x. Let's do BS on x. And we fix some x, and we want to find out if I can make my median at least x or not. How can I find the answer to this question? The point is that this binary search, this only happens when I'm solving the right parts. It only happens when Bn is equal to 0. So I have an array such that the last element is removed from it. And now I want to make the median of these parts at least x. In order to make the median of this part at least x, I need to make sure that more than half of these elements are at least x. I need to make sure that more than half of these elements are at least x. So if I want to make sure that at least half of them, more than half of them are x, the best half that can be, the best elements that can become more than x, greater than or equal to x, are these elements which are already higher than the other ones, which are already greater than the other ones, because it's easier to make them greater than or equal to x compared to the other elements. So it's better to try to make these elements greater than or equal to x. And when you want to do that, you need to just find some of these elements are already greater than or equal to x. They are good. But some are smaller than x right now. I need to find all these elements in here that are smaller than x and make them equal to x. This is the least I have to do. Is it clear so far? This problem is problem C. Is it clear so far? So I'm saying that, okay, I have chosen Bn, and Bn is equal to, B sub n is equal to 0. And now what I'm saying is that I need to now maximize my median, because an cannot be increased. My median should become some x, some maximum value x. And when I want to maximize my median, what I can do is to just try to make at least half of the numbers, more than half of the numbers, at least x. More than half of the numbers must become at least x. So I can say that I can say that the best half, I will get back to your comments, but for a second I come here. I say that more than half of elements here must be at least x. The best possible elements that can be greater than or equal to x are these elements, which are already higher. You can try to also make these ones greater than or equal to x, but these are already lower, and we just need these many elements to be at least x. So it's better if you choose the ones that are maximum already, the ones that are greater already, because our work will be easier. And from them, some of them are already greater than or equal to x, and some are not. Some are smaller than x, so they need help. I need to increase them. I need to make them at least x. So I will find this interval that these elements are at least x. These elements are less than x. They need to be increased to become at least x. Okay. Now let's get back to your comments. Yes, I will discuss this. I'm saying that they need to become at least x, but I will discuss if we can make them x or not. But what will be, that's again the same question. What if you cannot increase? Again the same question. I am saying that binary search on maximum median can be achieved. Yes. Yes. Yes, and you're right. Yes. I will discuss. I will discuss that. What happens if some b in here is 0? So, is it clear so far? Yes, I will discuss. If there is some bi here, that bi is 0, I must replace that element with some element from left. That bi is 1. I will discuss it. But all I'm saying is that you need to, there are some elements that are already x, and you need to find the rest of the elements that are needed. Let me get back to tablets. So you're right, if this bi, if a bi here is 0, I need to replace it by some element in here which bi is 1. So in other words, I should see that how many elements are already greater than or equal to x. From the rest of them, I need to make many of the others as much as I can greater than or equal to x as well. So we'll talk about that. But I need to just first make sure that you're okay with the fact that I want to, when I want to make my median at least x, at least half of the numbers here must be at least x. Okay. First, let me explain it, and then we can talk if we can draw a run on a real test case or not. So yeah, so this is what I want to do. Some elements are already greater than or equal to x, and from the rest I want to make some greater than or equal to x as well. So my question can be viewed like this. My solution can be viewed like this. I can say that when this last element will be removed, as you said, as you were mentioning, some elements are already greater than or equal to 0. So I can have two vectors for elements in here, the ones such that b sub I is 0 and the ones that b sub I is equal to 1. If b sub I is 0, we cannot do anything for that one. So they must already be greater than or equal to x. So do not forget that I have fixed x. Okay, I used a binary search on x, and now I know that what is my value of x. So if bi is equal to 0, already it is greater than or equal to x. So some of them are already greater than or equal to x, and I'm sure about I'm okay with that. So now if the number of these ones is, for example, some value like u, from bi is equal to 1, I know that because I know that I have n half elements, I have n minus 1 elements, at least, I mean more than half of them must be chosen. So the number of elements that must be chosen is gonna be at least floor of n minus 1 half plus 1. I must have at least these many elements greater than or equal to x. This is more than half. More than half of the elements must be greater than or equal to x if my median is gonna be greater than or equal to x. So at least these many elements must be greater than or equal to x. So let's say that this is m. Let's call it m. So I need to have m minus u elements in here such that they are gonna be greater than or equal to x. And if I want to choose m minus u elements such that they are gonna be greater than or equal to x, it's always best that if I have, for example, vector of all the elements such that b sub I is equal to 1, I need a suffix of them. Because these elements are already greater, so I need to choose the last m minus u elements and make them greater than or equal to x. Is it clear so far? Yes, this problem has a lot of detail. This problem has a lot of detail. It has a lot of detail in implementation, etc. But yeah, it doesn't have very very intelligent idea. It's mostly about considering all the cases and implement all of them, etc. So I'm saying that all the elements that bi is equal to 0 are already greater than, they must be already greater than or equal to x, otherwise they cannot help. So there are u of them. From the rest of them, there is m minus u elements. They must be a suffix of the ones with b sub I equal to 1. So I know that I have this suffix and I want to make all of them to be at least x. What I can do is to find out which one of them are already x again in here. Some part of the suffix is already x at least, x. But the rest of them, using a prefix sums, I can see that, for example, there are L elements in here. Their sum is already S. And each one of them are less than X. So how many operations do I need in here? The operations that I do need is X times L, because at the end their sum must become L times X. All of them will be X at the end. Minus this S. I need these many operations. And these many operations, the number of these operations should be less than or equal to K. Okay. And if that happens, then I can make median x. Otherwise, I cannot. And this way, my final order, my final time complexity is going to be n log squared, because as you see, I used two binary searches. First, I used a binary search on x. I have fixed the value of x, and then on bi equal to zeros, first I use a binary search. These two binary searches that I will talk about afterwards, I mean, these are independent. So first of all, I have a log in here. I have another log in here to find out how many of these elements are greater than or equal to x. And do not forget that in these vectors, I do not store bn, because bn will be removed. So I have a log in here for binary search, plus some log in here to find this interval that these values are less than x. So I know that these are the last m minus u elements, but some suffix of it is already greater than or equal to x. I find this with the binary search. I will be left with these parts. And in these parts, I can say that what is the current sum, what is the current prefix sum, and then I can say that if all of them are less than x, all of them should turn into x. So at the end, the sum will be L minus x. Initially, the sum is s, so I need these many operations. This must be less than or equal to k. And this way I can find out if I can make my median x. And then I can do this binary search and I can find the maximum x. Is it clear? No, the point is that I chose an interval such that I know that all these elements are less than x already. All these elements are right now less than x. So I want to find out that how many operations do I need to make them all equal to x. What is the minimum? Because at least all of them must become x. And the operations needed to make all of them x must be at most k. So I need to see that what is their sum right now, and what is the difference between their sum right now and L times x. And this difference must not be greater than k, because if it is, then there's no chance, there's no way that I can make all of them x. Okay. But yes, in the final answer, maybe I will have some additional operations as well, and I can make some of them greater than x. That's okay, but I do not need it. I just want to see that what is the minimum I need. And the number of operations I need to have the minimum I want must be less than or equal to k. Is it clear? Yes, I agree. It was such a huge jump in difficulty from problem B to C. And I think we spent around an hour to explain this problem. I hope that it was clear. We should, I was okay, yeah. Yes, because it's hard to implement, I agree. This problem is mostly about implementation. After finding the max median with binary search, we should also compare it with the median plus. Yes, exactly. At the end, that is exactly correct. After finding the max median with binary search, we should also compare it with the median plus largest AI, such that bi is equal to 1, that value plus k. Yes. So there's only one thing left. We can also see the code. I have not personally implemented the code, but maybe we can see the code of some people if it is open right now. But there's only one thing left that I must also say, and that's it. There's also one other case that is very similar, but you need to also find this out. This is just another burden of implementation, but it has no idea, this part again. The same thing goes on if we want to choose the right median with one of the elements from the left, and again, if the maximum, if this one is equal to 1, we said that, okay, we will choose this one and add k to it. But if it is 0, if b of floor of n half is equal to 0, again, we must consider two cases. The first case is that we find the maximum I such that bi is equal to 1 and choose that one with right median and add k to it. The second case is if we choose b of a of n half and we try to maximize our median. So we want to find the maximum median we can. This is the case where we will choose from the left side. So in this case, I'm sure that n half is removed. So in this case, I will not add n half to my vectors. Again, I will have two vectors for bi equal to 0, for bi equal to 1. It's like two vectors. N half is not going to be in these two vectors. All the remaining elements will be. N half will not be, because I'm sure that I chose n half. I mean, I'm sure that because if n half was 1, b of n half was 1, I would never come to this case. This is the case that b of n half is 0 and that one is chosen as ai and it is not changeable. You cannot change it. So again, when we want to fix some x, we will find that how many values are greater than or equal to x in bi equal to 0s. Using a binary search, we find them out. And if there are u of them, you will need to choose m minus u from here, m minus u from here. This looks like x. If there are u in here, you need to choose m minus u in here. And again, you need to do, if from this m minus u last elements, you need to do a binary search, find the ones that are already greater than or equal to x. And these ones are already less than x. And you need to see what is their sum again. And see that Lx minus S must be less than or equal to k. And again, that's almost the same thing about, almost the same thing as the case where we choose Bn and Bn is 0. So this is again a burden for implementation, but nothing new algorithmically. Okay. So if it is clear, do you want me to also show you some code? I have not implemented it, but I can show you some code if you want, or skip to problem D. Which one do you prefer? I'm okay with both. Whichever most of you prefer, we can do that. Code. Let me show you chats. Okay. So yeah, so we will see some code for it, sure. Let me bring some code. Let me search for some code. And see who has implemented it in a good way. Let me see. Okay, this seems like a good code. This seems like a good code. So, it's like, you know, in here again, you see those binary searches. Let's see what exactly he's done. It has some T. Let me make it full screen. So, for each test case, seeing nk, seeing ai, and bi's, and he, as we were discussing here, has two vectors for the ones which bi is 0 and the ones that bi is 1, and push back ai and bi in a general vector as well, and source these vectors. And m1 equal to n minus n half is going to be the index of, I think, the index that we're looking for. So these two gets, I think, are for the two cases that we have, choosing one from the left side and choosing one from the right side. Let me tell you something. You can view this part as like you have two arrays. I mean, we said that there are two medians. You can maybe view it like we have two arrays. Either, I mean, this is your first array, and this is your second array, and you will remove one element from one of these two arrays, and this way it might look simpler. Each time you will choose the last one of them. If b of the last one was 1, then you're good, everything is good. Otherwise you should search for the last one that is 1, and also consider that if it is gonna be 0, and if you're gonna choose this one, try to make the median at least x. This way maybe you can add some things, some cases with the same code. I mean, have some function and do not really implement all these cases individually. I think maybe he has done the same thing. If you take a look at this get, let me first see that he has a vector as well. If f of I dot second is 1, okay, so he considers all the cases that we have some ai such that bi is equal to 1. If bi is equal to 1, he considers that, okay, let's say we choose this one. He do not just consider the greatest ones, because it has no harm if we do it for everyone. Even though we know that many of them cannot be the best case, but because it's easy to calculate, you can just take maximum for all of them. There's no issue with that. So he just considers the maximum for all of them such that their bi is equal to 1. And otherwise, if they are in the first section, he says that ans is equal to maximum of ans and vec of I dot first plus L1. Otherwise, ans is equal to max of vec of I dot first plus L2. I think that this L1 and L2 is pre-processed values for the maximum median that you can have. So I think this guess will return the maximum median using a binary search. So in here we have a binary search and we have a 4 on all the elements. In v dot says v were the ones such that bi is equal to 1. We have a 4 on all of them. Okay, yeah, that makes sense. Yes, that can simplify the solution. We can have a 4, not even a binary search. Even having a 4 is okay. Even having a 4 is gonna be okay, I think. Because it's only one case. Yes. Okay, let me first continue, and then upper bound of v2, and how many of them are greater than these elements. Yes. So the point is that the thing that he has done is that he said that, and the point is that x is a binary search. It's going to be log of n. So the point is that x will be executed log of n times. So it's okay if we have a 4 on all the elements. I mean, for these parts that I said we can use prefix sums and binary search, you could also do a 4, do a simple 4. That's also okay. Because the point is that x is executed log n times for binary search, and this whole process will be done only once. Okay, you're not gonna do it many times. So you have only one binary search on x, which takes log of n, and in any of these binary searches, you can have a 4. You can have a 4 on all these m minus u elements, and if they were less than x, you can add some x minus that element to your sum. So the point is that this second binary search could also be simple 4s, simple loops. So it's also okay that if you do not use prefix sums and binary search in here, you can also just have a simple 4. Do you agree with this? So this was something that was happening in this code. So what I'm saying is that when you have a BS on X, because this BS will be executed only once. I mean, you only once have a BS on X. You do not do it, for example, like for every element. You only do this BS on X only once. So if you want to make everything So this BS that will happen only once will take log of n iterations, and if you have 4 on these two vectors, you have vec of 0 and you have vec of 1. The ones that their b is 0, the ones that their b is 1. We said that, okay, if we have u elements from here, we need to search for m minus u elements in here. And for these elements, we can just have a 4 and see if they are less than x. We can add them to become at least x. This way it will be simpler. Just we can get rid of that prefix sums and binary sets and make everything a bit simpler. Is it clear? Does it make sense? About the guideline questions that you're asking, maybe it's not a good time for discussing them because we're in the middle of discussing contest. But if you want to watch guideline videos, I just send you a link for guideline videos that I've made so far, especially for newbie rating. If you want, you can watch that. But for now, let's focus on this contest. Is it clear? Is everything clear? Shall we now end this problem and then move on to the next problem? Awesome. Did you understood it? Did you understand it perfectly? I mean, or is there any doubts still? I hope that you have perfectly understood it. Awesome. But I agree that I didn't also like this problem a lot. I would prefer it if it would be something else. And it was a huge gap between B and C. Even in our explanation, B took around maybe 5 minutes to 10 minutes, but this C took a lot of time. Okay, awesome. Guys, if you like the live stream, I would appreciate it if you can support my work by liking the video or subscribing to the channel. Is there anyone this live stream is his first live stream? Can all of you say that approximately how many of my live streams have you watched so far? It is your first live stream that you're watching from this channel? Okay, cool. Cool. So almost all of you have watched several live streams. Is there anyone it's his first live stream, is the first time that he's in here? I see. Interesting. And guys, if you had any further questions about any of these problems, etc., you are more than welcome to join our Telegram channel or our Discord server. We will have further discussions there. It is nice to see all of you here. First time because I always miss it. I see. Interesting. So, shall we move on to problem D now? Let's see if D takes less time or not. Because basically D must be harder, but let's see what happens on D. On problem D also, I think I have solution. It was a shame that I couldn't participate in the contest because as I see, it seems like I had solutions for problems very fast. But let's see what we can say about problem D. So problem D says that you have a farmer. There's a farmer and he has 2 cows, and they are playing on a graph, and they play like this. The first cow, each time there are n points, n vertices, and there are some edges. There is an edge. There are n-1 edges, bridges. That bridge number I connects island I to island I plus 1 for all I from 1 to n-1. And additionally, there are m alternative bridges that connect several of these vertices, several of these islands, and the first cow can use both of the bridges, but the second cow, Bessie, Elsie can use both of them. Bessie can only use main bridges. So Bessie can each time only move forward by one. And all the bridges are one way and can only be used to travel from an island with a lower index to an island with a higher index. Now, Elsie starts on island 1, Bessie can start on island S. Bessie starts on island S, and they will alternate turns. And each time, first Bessie starts. First Bessie doesn't move, then Elsie doesn't move. Then Bessie doesn't move, then Elsie doesn't move. And we know that Bessie can only use the main edges, but Elsie can use all the edges. Whenever a cow leaves a vertex, leaves an island, that island will explode and that cannot be used anymore. And even if the other cow is in that one, that cow will lose. And so that island will be exploded and no one can use it anymore. So maybe the other cow will be blocked from reaching the final vertex. So she will lose. So the point is that who will win if they both play optimally? About Bessie, playing optimally does not make any sense, because Bessie each time has only one way. She should just go forward one by one. But about Elsie, it's important to find what is the strategy. And for each S from 1 to n-1, you should determine whether Bessie wins if she starts the race on island S, or will lose if she starts the race on island S. So you need to say that who will win the game if they play like this. Salam. Okay, so let's see that what we can say. So n is up to 2 times 10 to the 5th, and m is also up to 2 times 10 to the 5th. Well, my main idea on this problem is this. We have these n islands. We have these n islands, and the point is that if Elsie is gonna win, if Elsie is gonna win, there must be some jump such that Elsie will jump over Bessie. So Bessie will move one by one like this, and there must be some jump over Bessie that Elsie previously was before Bessie, but after this jump goes after Bessie. This is the only way that Elsie can win. Right? Do you agree with this? So I'm saying that if Elsie is going to win, there must be a jump. That in which Elsie will jump over Bessie. So let's talk about these jumps. Well, first of all, I say that for Elsie, it's always optimal if she's gonna do this jump. It's optimal. As a fact, I can say that if Elsie is gonna do the jump, it is always optimal to do it ASAP, to do it as soon as possible. It's always optimal to do it as soon as possible. So the point is that if Elsie is gonna do this specific jump, and this is gonna be the jump that she will pass over Bessie, it's the best to reach this point as soon as possible and then do the jump over the head of Bessie. So maybe initially we can run a BFS on the original graph and see that what is the first time that we can reach any points. Why it is always the best to do this jump at the first possible time? Why it is always the best to find the shortest path from 1 to this point, because if you do it later, Bessie does more moves, and definitely that's not gonna be better. It's better if we're gonna jump over Bessie, we do it as soon as possible, because as time passes, Bessie will move forward, so the path that Bessie will have will become longer and longer, and more vertices will be exploded, and Bessie will go more forward. So the point is that if we're gonna do this jump, is always the best to do it as soon as possible. So that's why I can run a BFS initially and find out what is the soonest time that I can get to here for each jump. And then I see that, okay, for this specific edge, alternative edge, I'm considering the case that this is gonna be the jump that I'm gonna jump over the head of Bessie and win the game. So if I find the first time that I can get to here, assume that this is time t that I can get to here, and the next time I'm gonna be here. So if I come here at time t, I know that Bessie will visit t plus 1 vertices before I get here. Okay, so if or in other words, if the distance was to here was t, it means that I've done t operations, I've done t moves. So this is my t plus 1 move. So before I do my move number t plus 1, Bessie does t plus 1 moves. So Bessie has moved forward t plus 1 times. So it's like she has visited t plus 2 vertices. So Bessie has visited t plus 2 vertices. She has done t plus 1 moves. Let's see what is your comments. Isn't LC's most optimal route the one defined with Dijkstra from 1 to the final destination? We don't need Dijkstra because this graph is not weighted. All the edges have weight 1, so we do not need Dijkstra. We can just use the BFS. You know, when we have a graph that is not weighted, we can just run BFS to find the shortest distances. The way you will also find the earliest jump possible. Yes. I'll do the exact same thing, just instead of Dijkstra, I use BFS. And about the difficulty of problem C, I'm not sure what the rating would be. Maybe around 1900, 1800, I think, maybe. So if Bessie can come here at time t, and then her t plus 1 move, her move at time t plus 1 will be to here, Bessie in the meantime does exactly t plus 1 moves and visits t plus 2 vertices, right? So what are the vertices that can Bessie start from? And if she starts from those points, I can jump over her using this edge and will win the game. The point is that Bessie must start from some point in here, such that if even she does t plus 1 moves after that, she doesn't reach this vertex. So if the starting point of Bessie is some point in here, such that these indices are after t, so I should find all x's such that x is greater than t, so these points are not exploded, and also x plus t plus 1 must be less than this point. Sorry, I should change this from t. Let's assume that the index of this vertex is u. T was the time, so the index of this vertex is u, the index of this vertex is v. These vertices are u and v, and I will come to vertex u at time t. So x must be greater than u, not t. X must be greater than u, the vertex that I will visit here. And also x plus t plus 1 must be less than v. Okay. For all such x's, these x's will form an interval And I can say that for all the vertices in that interval, I can say that these vertices, in these vertices, Bessie will not win. So I can set the result of all these vertices to 0, because Bessie cannot win anymore. How can I set them equal to 0? I can either use a segment tree or simpler than that. We do not need to do anything online. We can do everything offline. When things do not need to be online, they can be offline. We can simply use prefix sums. We can easily use prefix sums. Just add 1 to here. I mean, if we want to set, if we have some interval from L to R, and we want to set their answer equal to 0. And let's say LR is inclusive exclusive. LR is inclusive exclusive. I will just add 1 to rest of L, and I will subtract 1 from rest of R. At the end, I'll add 1. I add rest of I minus 1 to rest of I. I have a 4 and add rest of I minus 1 to rest of I. 4 I from 1 to n. And then I'll say that if rest of I is greater than 0 for some I, if rest of I is greater than 0, then the answer is 0, else the answer is 1. So using a prefix sum, so do not forget that when you are working with offline, and I mean the operations on the intervals are offline, you do not need to use segment tree, etc. You can just use prefix sums. Okay? So this way I can just say that, okay, this interval of vertices in this interval, due to this edge, this interval cannot work anymore for Bessie, and Bessie will lose if it's starting from here. And I have several intervals. I set each of these intervals to, I say that in each of these intervals, Bessie will lose. And I can do that with simply using using prefix sums. And this way, this problem will be solved. Is it clear? If you're okay with that, please again put a plus or use this emoji. Otherwise, let me know to explain any particular. You can use this emoji, I don't know why it doesn't work, or put a plus. Awesome, shall we move on to problem E1 and E2? Awesome. So, okay, now let's move on to problem E1 and E2. Let me first bring them. And my lights are not turned off yet. I don't know when they're gonna do that. I think around after 2 hours they start to turn off. But so far everything is good. So, let's talk about problem E1. Problem E1. So, this is the easy version of the problem. The only difference is that x equal to n. We will see what x is. So, in this problem, you are given two integers n and x, and we will define f of I as follows. Suppose that we have a set s equal to 1, 2 to I. In each operation, you have to select an integer L from s such that L is not the largest element of s, and consider that element and the element after it. So you can choose, it's like you will choose two consecutive elements. You will choose some L and such that they are not, it is not the greatest one, and choose that one and the one greater than that. So it's like each time you will choose two consecutive indices in your set, and you will remove one of them. If their value is not equal, if the values are not equal, you will remove the minimum one. So if AL is greater than AR, if A sub L is greater than A sub R, you will remove AR and add AR to AL. If AL is less than AR, you will remove AL and add its value to AR. And if they are equal, you can choose either one of them and remove them. So f of I denotes the number of integer j's that at the end I can have s equal to j. So j can be the only element that remains after I minus 1 operations. So you need to find for each integer from I from x to n, you need to find f of I. And since x in this problem, E1, x is always equal to n, basically what this problem is saying is to just tell me that what is the answer for f of n. So it's just telling you that if you start with all the indices from 1 to n, and each time you can do these operations, which indices can be left at the end. So let's discuss it. Well, first of all, I say that a set of numbers are not good if and only if this happens. If there exists, if for an element there exists a block, if for any element you can find a block such that the sum of the elements in this block, assume that the sum of the elements in this block is equal to some s, and s is less than both of the two adjacent elements of this block. So for example, you have some x in here and you have some y in here, and you have some block in between them, and the sum of this block s is less than x and s is less than y. If this happens, none of these indices can be left at the end. Because at some point, you know, it's like each time you choose two elements and merge them. This is what is happening. You choose two elements and merge them. The minimum one will be removed, the greater one remains, or if they are equal, either one can remain. So what we are sorting in res, I think you're talking about another problem. So why are we storing in res? Which problem are we talking about? So okay, so I'm saying that s must be less than x and s must be less than y. If this happens, both should happen. Both of these should be hold. If this happens, none of these elements in the middle can be our answer, can be the last index that remains. Do you agree with this? This is the only condition. This is the only condition needed for any of the elements to, if we want, for them to not be able to remain at the end. Okay, so this is necessary and sufficient. If an element can remain at the end if and only if no such block exists. And it is very easy to prove. We are at problem E1. Is it clear for you guys? First, let me see that what is your feeling about it. Are you okay with this? If you are okay, please use this emoji or put a plus in the chat here. So all I'm saying is that if there exists such a block, well, there's no way to save these elements, because at some point they need to be merged with these two elements, with either one of these two elements. And at that point, whatever index that is left in here, that index will be removed, because because it cannot be merged with these two elements, and none of these elements can be merged with any of these two elements and not be removed. Because even if they already have the sum of all the elements in here, at some point they need to be merged with these two. They can at most be the sum of all the elements in here. And even if that sum is less than these two elements, then there's no way that they can remain after an operation. So now, if this does not happen for an element, the point is that you can always, such a block never exists for an element. That element is never inside such a block. Oh, I didn't show my screen. So the point was that if such a block exists, at some point we need to merge it with one of these two index elements, and it is not possible to do that because at most it has the sum of all these elements, and even the sum of all these elements is less than both of these two elements. So there's nothing we can do. But if no such block exists for an element, always I can start from this index and always just consider the first element to the right of it and to the left of it. At least one of them are less than or equal to the sum of the block that I already own. So I merge these two. Again, I have a block in here and I have two adjacent vertices. One of these two can be merged with them and this index can remain. This index I can remain. So I will merge it with that one. Again, so I can continue expanding my reach and one by one be merged with all of these elements and be remained as the only index. So if no such block exists for them, they will remain, they can be remained forever. So I need to find out if such a block exists for an I or not. So now I say that let's sort all the elements by their value and add them one by one. I'm not changing the ordering. I'm not changing the ordering of the original array. I'm just saying that let's sort all the elements by their value and add them to array and add them to the array one by one. One by one. So what happens if we do this? Each time a new element will be added, right now we have several blocks. When you add these elements, assume that there is a block already in here, and there's also a block already in here. Well, if, for example, let's consider one of these blocks, and maybe one of these blocks does not exist right now. Maybe, for example, there is an element here that is greater than our current elements, and this is not added yet, so there is no block to the right side yet. So when we consider an adjacent block, there are two cases. We assume that we know the sum of this block. It is S and this is AI. Well, I know that if S is less than AI, this block is done. There's nothing we can do for it. I mean, none of these indices can remain. Because for these indices, we are sure that this block is really blocked by the elements to the right and left of them, to the left and right of them. Because there is also another element in here that is not added yet. And that one is even greater than or equal to AI. So really, in the two sides of these blocks, there are numbers greater than the sum of this block. So what we cannot do nothing about it. We cannot fix it, and I can just make sure, I can just say that okay, none of these values in this block can work anymore. So I will remove them from my answers. I can both again use prefix sums to remove them, because it is similar to problem D. What we said in problem D, we're removing an interval, or I can remove them from a set, or I can use segments. All of them work. So anyway, I can say that none of these values can work in this case, but if S is greater than or equal to AI, the point is they can still be alive. They can, because they can eat AI. By eating, I mean that they can be merged with AI, and because they're greater than or equal to AI, their index can remain. I mean, whatever is the index that they had, that remains. So in this case, only AI can survive, because there's a fact. When AI will be added, these parts will be merged, and the point is that AI always has the chance to eat all of these elements, because all of these elements individually are less than AI. So AI can start and one by one eat them one by one. And this way it can be merged with all of them and have this block and be as the representative of this block, and this block has some S plus AI. So AI can always survive. So about AI we have no doubts. We know that it will survive. But about these ones we have doubts. That's why we check the sum of them and compare it with a sub I. So what I do say is that if in this case only AI can survive, and in this resulting block that we will form in here, only AI can be the representative in the future. But in this case, that S is greater than or equal to AI can survive still, and these ones will remain alive as well. I mean, the ones that already survived still can survive. So the point is, if this sum is greater than or equal to AI, they can still survive. And when we merge these two components, the new sum that these components have is going to be S plus A sub I. Okay. So is it clear so far? Please use emojis or put a plus in the chats and show me if it is clear for you. Okay, this light finally turned off. How long did it take time? Around 2 hours. Okay, sorry for the oh, you cannot see anything, I guess. Let me see if I can make it better. Okay, now it must be better. Let me change. Okay. So, is it clear? Again, please use a plus or use the emoji to let me know if it is clear so far. I'm on another problem. Right now I'm discussing problem E1. I cannot jump to that one. Okay, awesome. So yeah, so this is the case where that we have. So we add elements one by one, and sometimes we will remove some of the elements. We kill some of the elements. We say that, okay, this element is added. This element itself is greater than this block. And this block, we know that this element before it is not already added as well. So if it is AI, this is even greater than AI, greater or equal to AI. So this block will be killed if AI is greater than its sum. At the end, the ones that will survive are going to be our answer. So at the end, we will see that which ones are not deleted and they can survive. So this is how we can solve E1. E1 will be solved like this. And our time complexity is going to we have n operations, and each time we can merge them. For merging, again, we can use segment tree, or we can use DSU, or we can use any of these ideas. So our merging is going to be n log n. Around n log n. We can easily do it in n log n. We can just merge them and save all the indices, and we can remove the indices if needed. Okay. So this way things can be calculated. And if both sides, in both sides, we had blocks, we will first individually find the answers for both sides. If this side can survive or not, if this side can survive or not, and then we will merge these two sides together. So this is what I had in mind for problem E1. And when we have problem E2, again, I did not finalize my solution on E2, but on E2, let me first show you what is the statement. On problem E2, the only difference is that we need to print everything from 1 to n. We need to print f of 1, f of 2 to f of n. That was what I was thinking before the live stream on how we can solve this. I think I did not finalize it, but what I had in mind was that when you remove some elements, you can see that what was the amount that they needed. When you remove some elements in our solution in E1, you can just keep that what was the value that we needed in this interval. I mean, for example, they needed x more. they needed their sum to be more by x, for example. And you can save that for any indices, that's how much more they need. And then when you add a new element to your array, I mean, assume that we're adding elements one by one. For example, we solved f of I, and now we're solving f of I plus 1. We're adding elements one by one. So when I plus 1 is being added, what we can do is to see that there are again two cases. Either it is less than the previous elements. In that case, it cannot survive for sure. So there are two things you need to find out. If this one can survive or not, and this if the previous ones can be. The ones that can connect with it can survive or not. If this one is less than the one before it, it cannot survive. It is greater than or equal to the one before it, it might survive. It depends on this block that was removed for the previous one. So if it is less than this one, we're sure that this cannot survive. Otherwise, it depends on some situation before that we will consider now. And the point is that if you just keep for every element in a segment, for example, keep that, okay, they needed x more, the sum must have been more by x such that they could survive. If it is 0, it means that they already can survive. And if it is some x, it means that they must be increased by at least x so that if they survive. And if this value is for example ai, and if ai is at least x, the point is that this can be merged with this interval. And it can increase this value by a sub I. If a sub y is greater or equal to x, the point is that this block will not be removed anymore. And some values might survive in here. And again, there are two cases. Well, if ai is less than these elements, well, we know that ai itself cannot survive. But maybe it helps these elements here to survive. So each one of them have some value like x, such that they need this much to be able to survive. And we can make some changes and make maybe what they needed will be satisfied, and they can survive this way. And this way we can just update these ones. And for this one itself also we can see that what was the values in these blocks, what was the maximum value that they needed to survive in future. And if ai is at least that much, ai might survive as well at the end. So it might look like a very, very rough idea. It is not very precise because I have not finalized everything on this. But this is the main idea I had in this problem, was that when I add an element, I somehow have some clue about how much these elements need to be added by in order to being able to survive. And it helps me to determine that when a new element will be added, can it survive till the end or not? And can the elements before it use this element to survive or not? So it is not very precise, sorry for that, but I hope that it can help. Is it clear what I'm telling you? Do you have any questions about it? Okay, I guess that there are no questions about it. So thank you again for joining this live stream. Let me see that the next contest is tomorrow. Interesting. And it's div 1 plus div 2. So maybe we will have another live stream tomorrow. So it's gonna be the third day in a row that we're gonna have streams. Yesterday we had our weekly topic streams. Today we had this stream, and tomorrow we also have a stream. And then the next one is the div 3 days from now. So I think I see you tomorrow then. Can I summarize the case in C? I think, yeah, I can tell you a little bit, but I really recommend you to watch that part again. I can summarize once again that's what was this case, but I really recommend you, because in here, as I said earlier, you can just choose any parts that you want and you can watch that part again. That's something that you can do easily. But yeah, I will explain you a little bit on and summarize the case where the largest element is not n, is not 1. Let me bring it in tablets once again. Let me for a second. So in the case where b sub I is 0, we know that in the case where b sub I is 0, b sub n is 0, we know that we cannot change it. So we need to maximize our median, which is some x, for example. So we need to maximize x such that our median will be at least x. We call that median x. And we know that there are two vectors, some vector of 0, which is all the elements such that their b is 0, and vector of 1, which is all the elements that their b is 1. When we want to make our median at least x, we need to find out how many elements are at least x in the first vector. For example, there are u elements that are at least x in my vector of 0, the ones that I cannot change. So that's all I have from them, because I cannot change them. If they're already greater than or equal to x, it's good. If not, I cannot do anything about them. So I have u elements greater than or equal to x in here. For the second vector, I can just do a simple for. On the greatest m minus u elements, I can have a for of O of n. I mean, even a for works. I do not even need binary search, because my general binary search on x takes log of n and will be executed only once. So I have the binary search that will be executed only once, and it's the number of its iterations is O of log n. So the point is that I have m minus u in here. I have m minus u elements, and I can have a 4 on them. M is the majority of the numbers. M is n minus 1 half plus 1. I know that at least these many elements must be at least x, so that my median is at least x. So I have a 4 on all these elements, and if they're already x, this is good. If they're not x, I see that what is x minus that value, and I will add that to my sum. And that sum must be at most k. If that sum is at most k, with k operations, I can make sure to turn every one of them into x. But if it's not, I cannot do anything. Okay, and this way I can just say that I can find out if I can make my median x or I cannot make my median x. So if b sub n is equal to 0, the main thing is that now I should make my median at least x. And how would I do this? I have two vectors, vec of 0 and vec of 1. On vec of 0, I see that how many elements are greater than or equal to x. On vec of 1, I see that I know that the rest of the elements must be from vec of 1. So I consider a suffix of vec of 1, and I see that how much do I need to add to them, to the values in this suffix, so that all of them will be at least x. Does it help? I hope that this resolves the issue. So you will still choose a of n even if bn. Yes, I consider the case of choosing an, but I also consider the case of if bn is 0, the case of choosing the maximum I such that bi is 1. I talked about all this. If b sub n is 0, there are two cases. If b sub n is 1, I'm done. I will choose n. But if b sub n is 0, there are two cases. Either I choose this one, or I choose the greatest one such that it is 1. Okay. Yeah, you're welcome. Thank you very much. I hope that this helps you. Any other specific questions about the contest? So yeah, and as I said, the recording will be here as well, so if you needed to watch any parts, you can watch all of them. And also do not forget our live streams, our live topic streams on Fridays from 12 to 14 GMT. And first I'll see you tomorrow, but in general I'll see you every Fridays on those topic streams. Thank you very much guys for joining. It was nice having you here today as well. I hope that we can continue it and learn together. Thank you very much guys. Goodbye.